So let's start with a number, 20 milliamps. That's it. I mean, what can you even do with that much current? It's just enough to maybe light up a tiny little LED. But what if you want to spin a motor or turn on a lamp in your house or, build a robot? With just 20 milliamps, it feels kind of impossible. And that tiny number, right there, is the biggest challenge for any microcontroller that wants to reach out and touch the real world. All right, so that brings us to what we're talking about today. In this explainer, we are going to tackle controlling the real world. We're going to figure out exactly how the tiny low-power brain of a microcontroller can learn to command the high-power muscles of the physical world. Here's the game plan. We'll kick things off by understanding the power gap. Then we'll meet our number one solution, the transistor. From there, we'll level up to controlling some really big loads with things like relays and motors, then get super precise with motion control, and finally, we'll dive into how to safely wrangle high-voltage AC power. Let's get into it. Okay, first things first, the power gap. This is really the heart of the problem. I want you to picture a microcontroller as this super genius brain, right? It can crunch numbers and make split-second decisions millions of times a second. But when it comes to physical strength, when it comes to its ability to actually push current, well, it's got no muscle. Yeah, your typical microcontroller I/O pin, it can push or pull about 20 milliamps. That's all you get. So if you want to drive anything that needs real power, a motor, a string of bright lights, you just can't hook it up directly. You need a middleman, something that can take that tiny whisper of a signal from the microcontroller and use it to control a much bigger flow of energy. We need an electronic switch, or an amplifier. And that middleman, that fundamental solution, is the transistor. If the microcontroller is our brain, the transistor is the very first piece of muscle we're going to give it. These tiny little devices are, and I'm not exaggerating here, the absolute bedrock of all modern electronics and power control. Now, they come in a couple of main flavors that we care about. On one side, you've got the bipolar junction transistor, or BJT. The easiest way to think of this is as a current-controlled amplifier. A tiny little stream of current going into its base pin opens up the floodgates for a much, much bigger current to flow through. Then you've got the field effect transistor, or FET. This one's different. It's a voltage-controlled switch. You just apply a little voltage to its gate, and that creates an electric field that lets the main current flow. And here's the magic part. It does this while drawing almost zero input current. Super efficient. Okay, let's see how this actually works. Take a look at circuit A. That switch, SW1, that's pretending to be our microcontroller's output pin. When it sends out a 5-volt signal, a little bit of current flows through that resistor and into the base of the BJT, Q1. And just like that, the transistor switches on, allowing a way bigger current to flow from the 12-volt supply right through the load. See? A tiny little signal is now in charge of a much more powerful circuit. Now check out the FET in circuit D. This is where you really see its advantage. When that switch closes and applies 5 volts to the gate of the FET, look at the input current. It's practically nothing. Because it has such a high input impedance, the FET doesn't put any strain on the microcontroller. It's just listening for the command. It's not demanding any power to do its job. Just incredibly efficient. So transistors are awesome for amplifying our signal. But what if we need to control something really big? Or, and this is super important, what if we need to keep our delicate little microcontroller totally and completely separate from a dangerous high-power circuit? It's time to bring in the heavy hitters. And that's where the relay comes in. I love relays because they're so elegantly simple. It's just a switch. But instead of flipping it with your finger, you flip it with an electromagnet. You energize a little coil, it creates a magnetic field, and that field physically pulls a metal arm over to close a completely separate, high-power circuit. The key phrase to remember here is complete electrical isolation. The two circuits never ever touch. And here it is in action. Up in the top left, our microcontroller sends a signal to that transistor, Q1. The transistor then acts as a smaller switch to turn on the relay's coil. When that coil gets juice, it closes the contacts and bam, our 12-volt lamp turns on. Oh, and you see that little diode, D1, across the coil? That is super important. When you turn the coil off, its magnetic field collapses and can create a nasty voltage spike that could kill our transistor. That diode basically catches that spike and snuffs it out. It's a critical little safety feature. All right, enough with just turning things on and off. Let's actually make something move. The classic DC motor. At its core, it's just a bunch of wires and magnets. You run a direct current through a coil of wire, it creates its own magnetic field, and that field pushes and pulls against other magnets, creating a force, a torque, that makes the whole thing spin. It's that simple. Electricity in, rotational motion out. But, just slamming a motor on or off is kind of clunky, right? What if we want to control how fast it spins? Or what if we needed to move to a very, very specific spot and just stop there? For that, we're going to need to get a little more clever. This brings us to one of my favorite tricks in all of digital electronics, pulse width modulation, or PWM. It sounds complicated, but the idea is brilliant. Instead of giving the motor a steady stream of power, you just pulse it. You turn the power on and off really, really fast, thousands of times a second. By changing how long it's on versus how long it's off, we call that the duty cycle, you can control the average power the motor gets. More on time, it goes faster. Less on time, it goes slower. It's an incredibly simple and precise way to control speed. And this is what that circuit looks like. Our microcontroller is spitting out that super fast on-off PWM signal. That signal goes right to the gate of our power FET, which we already know is a fantastic, fast switch. The FET then chops up that 12-volt supply and feeds those little pulses of power to the DC motor. So now just by changing a number in the code, the microcontroller has full, smooth, precise control over the motor's speed. Now for controlling position, we've got a couple of other specialized players. First up is this servo motor. Think of it as a DC motor that's smart. It has a built-in sensor that's always reporting its exact position back to the controller. This lets it move to a very precise angle and hold it there, even if something tries to push it. Then you have the stepper motor. This one's different. It moves in exact, repeatable little jumps or steps. It doesn't need feedback. You just tell it move 50 steps clockwise, and that is exactly what it does. As you can probably guess, controlling these is a bit more involved. As you can see here, both the servo and the stepper motor need these dedicated driver integrated circuits, or ICs. These chips are specialists. They handle all the complicated, low-level stuff, like reading the servo's feedback or sending the complex pulse sequences to the stepper's coils. This frees up our main microcontroller to just focus on the high-level commands, like go to 90 degrees. Okay, we've covered a ton of ground in the DC world. But what about the big leagues? What about the power that comes out of the wall socket in your house? Controlling high-voltage alternating current? Well, that's a whole different ballgame, and safety becomes the #1 priority. So, because AC current flows back and forth, a simple one-way switch like a transistor just won't cut it. It would only catch half the wave. For this, we need a special component called a triac. The best way to picture it is like two special switches, called thyristors, packaged together but facing opposite directions. This setup lets it grab and control the current as it flows both ways through that AC wave. And this is where we have to get really serious about safety. Look at the circuit in the bottom right. Our little 5-volt microcontroller is controlling a 240-volt lamp. How is that even possible without everything catching fire? The secret is that chip, U2, the opto-isolator. Inside that chip, a tiny LED on the microcontroller's side shines a beam of light across a physical air gap to a light sensor on the high-voltage side. There's literally no electrical connection. It's a bridge made of light. This isolation is absolutely critical to protect the low-voltage electronics and, more importantly, to protect you from that dangerous mains voltage. So, how do you dim a light with a triac? It's a really cool technique called phase angle control. The microcontroller watches the AC waveform as it goes up and down. Instead of turning the triac on right at the beginning of each wave, it waits for a tiny, calculated amount of time, the trigger time. By delaying when it turns on, it effectively chops a piece out of the waveform. The later it triggers, the bigger the piece it chops out, and the less power gets through to the lamp. This is exactly how most modern light dimmers work. All right, let's just quickly recap the journey. We started with the fundamental problem. Our microcontroller only has 20 milliamps to work with. We solved that by giving it digital muscle with transistors. We used relays when we needed to control massive loads with full electrical isolation. We figured out how to control DC motor speed with PWM and their position with servos and steppers. And finally, we found a safe, solid-state way to tame AC power with triacs. And I want to leave you with this piece of engineering wisdom because this quote just nails it. It really captures a core decision that engineers have to make every day. Do you solve a problem with a dedicated hardware chip? It'll cost you a bit more per unit, but it makes your software a lot simpler. Or do you try to do it all in software? The software itself is free to copy, but now your microcontroller is working overtime. This hardware versus software trade-off is at the heart of so many design choices. So there you have it. These components, transistors, relays, motors, triacs, they aren't just parts on a circuit board. They are the essential bridges that connect the digital world of code to the physical world of action. They are what allow a bunch of ones and zeros to actually make something happen. So I'll just leave you with this one question. Now that you know the tools, what would you build?